All right, the next example we have, example 3. We are to determine the flux of f equals x squared j hat through the surface generated by y equals 1 plus x squared plus z squared for y between 1 and 5. And we want to orient the surface S so that the normal vectors point in the negative y direction. Okay. So for this example, remember that flux is just a vector surface integral f dot ds. And if we want the flux through S, then we're going to integrate over S. Excuse me. So what we want to do here is ultimately we want to calculate this. And we have this function right here. So now notice that while this is not solved for z, it is solved for one of the variables. So we could definitely use the parameterization. We could let x equal u, z equal v, then the parameterization would be r of u comma v equals, this would be u, and then y would be 1 plus u squared plus v squared v. Right, so we could use that standard parameterization because y is expressed as a function of two other variables. So we could let the independent variables here be the independent parameters, and then that will allow us to express y in terms of u and v. So that's one way to do this. I would suggest a different approach, though, primarily because of the following. Notice that x squared and z squared, they're being added together. So there is definitely symmetry here via negative x and x. They both send to the same thing. Same thing for z. If you plug in a z value or negative that z value, it still goes to the same output. So there's symmetry in reflection about the x and z axes. So this sort of, to me, says there's some sort of circular symmetry. If our domain was given, like for x between 0 and something, or z between 0 and something, then we could probably parameterize it in the way I first suggested. But because the output is being constrained, it's going to be harder to do this in Cartesian. But really, I think what screams use polar coordinates or ideas of polar is the fact that we have variable squared plus another variable squared. That, to me, is the hallmark of when to use some sort of sine cosine type of parameterization. So I'm going to go ahead and run with that. So I'm going to go ahead and parameterize the surface S by setting x equal to v cosine u, y, excuse me, not y, but we'll leave that one alone for now, and setting z equal to v sine u. Now notice here, we know that y is equal to 1 plus x squared plus z squared, which simplifies down into 1 plus v squared. So I'd go ahead and make that our y component. All right, now that we have that, what is our range going to be? Well, we know, also we can say for, let's say, u comma v in, well, we know that u definitely goes between 0 and 2 pi, crossed with, let's go ahead and think here, we know that y is supposed to be between, 1 and 5. And we know that y is actually 1 plus v squared. So we can go ahead and deduce that v must be between 0 and 4. And since we're interpreting this v as a radius, we can go ahead and take the square root of both sides, taking the positive root. So v is between 0 and 2. Okay, so now that we have our parameterization along with our domain, again, this domain, I always forget to write this, but this is what we're going to say D, our domain D. So now what we can do is take our partial derivatives and cross them. So what I'll go ahead and do here for this one is, just since we can save some time here, we don't have to show all the steps out for these. I'll go ahead and just tell you that our U cross RV, this cross product is equal to negative 2v squared cosine U v comma negative 2v squared sine U. And notice that this v here, the y component, v, since v ranges over 0 to 2, this tells us that v is definitely not negative. But we want our normal vectors to be pointing in the negative y direction. So really, this is in the wrong direction. So what we should actually have chosen here is our v cross ru, in which case we get positive 2v squared cosine u, comma, negative v, comma, positive 2v squared sine u. Remember that all of the components they flip in sign. So let's erase the one that we don't want, and we'll take the normal vector that we do want. All right. With that, we can go ahead and set up this double integral. So the double integral, so this right here, I can just say, continuing, this would be the double integral over d we have our vector field. Our vector field is really just 0x squared 0. So this would be 0x squared. And on our parameterization, x is v cosine u. So this would be 0 comma v squared cosine squared u, comma 0, dotted with our normal vector, 2v squared cosine u, negative v, comma 2v squared sine u, dA, which will end up being either du dv or dv du, depending on the order that we choose to integrate this. So we'll do our dot product, so double integral over d, copy pasting. Here we should have negative v cubed cosine squared u dA, which we can go ahead and factor the negative out. And since there's no coupling between the variables and our domain of integration is a rectangle in the xy plane, we can actually split this up into a v integral times a u integral. And since this is we're integrating a cosine squared, we'll definitely want to make sure that we use the fact that this is equal to 1 plus the cosine of 2u over 2, the half angle identity. So I'll factor out the 1/2. So I'll make this 1/2, 1 plus cosine 2u du. All right, when we integrate 1, we will get u between 0 and 2 pi, which is 2 pi. When we integrate this, the cosine will turn into a sine, and then sine of 0 and sine of 2 pi, or 4 pi, because of this 2 here, is 0. So this will integrate to 0. All right. And because of this 1/2 here, it looks like this entire thing gets turned into a single pi. So this becomes negative pi, right? Because we have 2 pi divided by 2, and then this negative. Not only that, we're also going to integrate this term, which will give us a 1/4 v to the 4th between 0 and 2, which this will turn into a 2 to the 4th, which is 16. 16 divided by 4, we will have -4, so the answer here is -4 pi. So to interpret this really quickly, this is the first time that we've received a negative answer for flux. So what does this mean exactly? Well, I actually know what this looks like, so we can quickly graph this and kind of get a visualization of what's going on here. So here are the x and z axes. This particular shape is this right here is an elliptic paraboloid, which opens in the positive y direction. So it looks something like this. Something like that. Not the best drawing there, that's okay. Something like that. So yeah, it's an elliptic paraboloid. Trying desperately to make that looks a little better. It's an elliptic paraboloid that opens in the positive y direction. So something like that. It begins at a y value of 1. So we are integrating from y equals 1 right here all the way to, I mean, again, this extends forever. It continues onward. But we're going to stop at the plane y equals 5. So this right here would be y equals 5. So if our normal vector is oriented in the negative y direction, that means our normal vector looks something like this. So that's making a declaration saying this is this outside of the surface. So we're interested in how much of the vector field that's flowing through the surface, how much of it, like what's the net flux through this surface outward through this direction. So how many of the field lines are coming in and like poking outward like that? Something like that. Well, because we got a negative value, what this actually means is the net flux through this thing is actually in the opposite direction. It's more like the field's coming in and going through it like that in the opposite direction. Something like that. That's really what's going on here. The flow of the vector field is at least the net flux is in the opposite direction of this vector. It's coming into the surface, not exiting the surface like that.